So welcome. I'm very excited to introduce my colleague and friend, Kathy Pegion. I was kind of hoping that Ben would be here to do the introduction because he's way funnier than I am, but you're stuck with me. So Kathy and I met in 2013 on a trip to Taiwan. And basically it was just love at first sight. So we have collaborated a lot over the years. We had, of course, heard each other's names from various projects over the years, but Kathy graduated from Florida State with a degree in meteorology and computer science, and then went on for a master's there, and then spent 3 years working for NASA and for NOAA, and then went to graduate school at George Mason University, where her advisors were Shukla, who purely coincidentally was here yesterday. Now, let's trace back to where that butterfly flapped. and Ben Kurtman, our very own dean. So, without further ado, let's hear from Kathy, who is one of the most foremost experts on subseasonal to seasonal prediction, about this fun project we did, Sources of Predictability for Subseasonal Precipitation in South America. So take it away, Kathy.
Thank you, Emily. Yeah, it's really a joy to be here, so thank you all for coming. So I will say there's quite a few Becker, Kurtman, Pegion, Kurtman, Becker papers out there. When you find good people to work with, you just keep working with them. So this is another outcome of one of those collaborations. Yep. Okay. So. So I know that probably a lot of you here are familiar with subseasonal predictions, but I also know that the Rosenstiel School, many people work on a variety of topics. So I do want to make sure that I kind of orient you to what the focus of this study is. So subseasonal predictions, they sit in between our typical weather forecast and our seasonal forecast. And they're kind of a challenging area to be making predictions in, because the signal from our initial conditions from our weather forecast have kind of dropped off and they're not really playing a strong role at that point in time. By the time you get out to this 2 to 4 week subseasonal time scale. And the signal associated with our sea surface temperatures and other more slowly varying sources of predictability, that signal isn't very strong yet. And so we have this intermediate time frame where we kind of have a small signal and a lot of noise. And so now we're trying to figure out how to predict on that time scale. And really what happens is our predictions are best when we have multiple sources of predictability coming together to give us a stronger signal. And that can come from the land surface and its interaction with the atmosphere, bringing some memory from the soil moisture. That can come from persistent atmospheric variability that has a longer time scale, so it's giving us a little bit longer predictability. Or it can come from the stratosphere, it can come from the ocean, a variety of things coming together to give us skill on these time scales. So I'm showing you here from the subseasonal experiment the skill of temperature at a 3 week forecast from a bunch of different models. And then this is persistence, and then this is if you make a multi-model ensemble from all these models. And what you'll see when you look at the skill of temperature, if you come from the weather side of things, these skill scores are not very high. This is anomaly correlation. It's a measure of how well, over a whole bunch of forecasts, the ups and downs of the anomalies match the observation. So does the model say that we're going to have above normal temperature when we actually have above normal temperature, and below normal we're going to have below normal, and it quantifies those ups and downs. So if you come from the weather side of things, that's not a high correlation, but for a week 3 forecast, everything I'm showing you that's in color is at least statistically significant correlation. And you can see that for temperature, all the models show correlations that are statistically significant over most of the globe. Well, that's great, but precipitation is a quantity that really brings life to the world, right? It's the water resources for agriculture and many other aspects of life around the globe. And so we really need to be able to predict precipitation better. And you'll see here, if I show you the week 3 precipitation skill, I'm only showing you South America. And the reason I'm only showing you South America is because there is no statistically significant skill over the rest of the globe. The rest of everything will just be this yellow color for the most of the picture. So I'm only showing you South America. But we have one region where there is large enough region of coherent statistically significant skill in Brazil. You see this across a variety of models. So there's something going on here that all the models are picking up on as a source of skill in this region. So really this study is, where is this skill coming from? Why do we have skill here? And sort of the corollary, why do we not have it other places, right? Why is there skill here? If it's coming from some large-scale source of predictability, you would think that it would get skill from in other places. So where is this coming from? Is really what I'm after in this talk. So to give you an overview, I'm not an expert in South American precip skill, precip in general. I started studying this because I wanted to know where the skill was coming from. So I had to go look up, okay, what is the precip like in South America? This is showing you the annual rainfall, and you can see the sort of the Amazon region where you have the most rainfall. And then this shows you for each season the percentage of the annual total. So you can see the large majority of the rainfall in our region of interest falls during December, January, and February. And this is the monsoon season in this region. One of the main sources of precipitation in this region comes from the South American dipole. This is mostly on intraseasonal to seasonal timescales. And it's really a South Atlantic convergence zone sets up, and so you get precip where that sets up and enhanced precip, so more than normal precip. And then you get dry anomalies or less than normal precip adjacent to that. So you get this dipole pattern, and it can be in different signs throughout the season. It really has to do with where the South Atlantic convergence zone sets up. So that's one way in which we get precipitation variability in this region. When I first showed people those skill plots, everybody's like, oh, it's El Nino, it's INSO, it's nothing interesting, oh, yeah, whatever. But that's actually, I'm going to argue that's not the case. This is showing you sort of the sea surface temperatures associated with El Nino in the Pacific, and the impacts in South America are, of course, very local since it's right adjacent to the western coast. And then this is showing you for El Nino the composite precipitation anomalies. So you can see that actually there's only a little bit of an El Nino response there in our region of interest where we have skill. And you can see actually you get a bigger response up here, more in Venezuela, down here further south. And then La Nina is kind of a flipped sign. So I'm not sure that ENSO is necessarily the answer. Another thing, people are like, well, if it's not ENSO, it's got to be the MJO. It's not Julian oscillation, right? I mean, it's, everybody knows that it's ENSO or MJO is sort of the default, response to sources of predictability on these timescales. But I'm going to show you that that's actually not the case either. So how the non-Julian oscillation does affect precip in this area, MJO, the classic characteristic of the MJO is the eastward propagating convection, and that's represented in the blue here by the below normal LR anomalies, and then the above normal, the adjacent suppressed convection, and that eastward propagation over 30 to 60 days, and this is sort of categorized by 8 phases, basically. And for each of these phases, this study showed the precip composites associated with that. So you can see that in certain phases we have more and less rainfall in our region of interest. So that would be 1 in 5 phase. There's and then some in 6, 4 and 8 especially. So some aspects of the MJO is affecting our precipitation in this region. So thinking about all of that, I'm going to fundamentally ask, where is the subseasonal precipitation skill in Brazil coming from? I'm going to look at in terms of timescales. Is it interannual, subseasonal, primarily sources of predictability? What seasons are most important for this skill? Where is the skill coming from, the wet season or not? And then what components of the climate system are contributing most to the skill? Is it primarily coming from the atmosphere, the ocean, the land, combinations of them? And then which mechanisms are contributing to this skill? Is it the dipole, ENSO, and JO? Is there something else? Spoiler alert, there's something else. So I've been showing you skill, but I want to tell you where I'm getting that skill from. That skill is coming from sometimes called reforecast or hindcast. This is kind of an older term. This is the newer term. You'll see both listed. I call them time machine forecasts. We take today's model, we put it in a time machine. I know that's a really funny looking time machine. We take today's model and put it in a time machine, and we go back in time and we make a forecast as if we had today's modeling system back then. And then we can do that for many past times by providing the initial conditions at those different times. And then that will allow us to calculate robust statistics about the skill, because these things have already happened. We have the verification for that. If we were to just make forecasts from today going forward, we'd have to wait a long time till we had a lot of forecasts to have robust statistics. So we use these reforecasts or hindcasts to get our robust statistics of the skill of the system. So I'm showing you again, just to remind you, this is the skill from all of these different models for precipitation at week 3. Coming from the sub-X, you've heard it as sub-X, it's also called sub-C. We changed our name, but we're like Twitter, everyone's just going to keep calling us the name we were originally called. And these forecasts were, all of these reforecasts were initialized either weekly, or one of the models initializes every 5 days. They all run out from between about 32 and 45 days. They have a range of ensemble members, and we have a hindcast period from 99 to 2015 for most of them, with one of the models going out to 2020 for its hindcast. So that's where all the skill calculations are coming from. So first question, how much of the week 3 precipitation skill is driven by interannual variability? So really this gets at the whole, everybody thought, oh, the skill's coming from ENSO. Is it? Is it really coming from ENSO? If it is, then it's probably, that skill is really interannual component to this. So I removed the interannual variability and recalculated the skill. And you can see here we have some models that no longer have any skill. And I'll zoom in on a couple of those. First, this is the NSEP model, CFS2. When you remove the interannual variability, it loses all the skills. So some of the models lose all skill when interannual variability is removed. So this is telling us that that skill is driven by interannual sources in those particular models. But we also have some models that retain quite a lot of the skill once you remove the interannual variability. So that tells us that there are subseasonal sources of predictability, or at least something shorter time scale probably than the interannual, that are contributing to skill in these models. And the other thing you'll note is that when you remove the interannual variability, the skill associated with ENSO was more in Venezuela, and you'll see that that's actually where the skill is lost when you remove the interannual variability. So we're losing some of that ENSO contribution by removing the interannual variability. I do want to highlight this model is from NCAR. It's the CSM2 model, and it has the best skill overall, both with and without interannual variability. And they also have some unique experiments that I'm going to show you. So going forward, everything I'm going to show you is coming from the NCAR CSM2 model. So this is looking, so we sort of answered this question about interannual variability. It seems like at least for NCAR CSM2, there's some subseasonal source of predictability, a source of that skill. And so now I'm going to look at the question of, with that model, which seasons have the most skill. And so if I actually calculate the skill separated by season, you see most of the skill is coming during DJF, the monsoon season, or SON, which is also kind of the early part of the monsoon season. And I'm going to focus on DJF for the rest of this talk, just for time, and focus similar results come from SON as well. So we figured out that there's some sort of subseasonal source of predictability. We figured out that we're going to look at the DJF. So now we kind of want to identify what components of the climate system are contributing most to this skill. Is it the atmosphere, the ocean, or the land? And so to do this is the unique set of experiments that NCAR has with this model. I've been showing you skill from what I'm calling the control experiment. And in that experiment, the atmosphere, the ocean, and the land initial conditions were realistic, and the model of regular forecast was made off of these realistic initial conditions. But they've done a whole suite of additional experiments where they play around with the initial conditions of different components. So for example, they have an experiment called ATM, for atmosphere, where they set the atmospheric initial conditions to climatology. So they just take the average atmospheric initial conditions for a given date. But then they set the ocean and the land initial conditions to realistic initial conditions. And they've done every combination of that with the atmosphere, the ocean, and the land, as well as combinations of atmosphere, land, ocean, land, and then also setting all of the components, initial conditions to climatology. So in a coupled system, it is really hard to separate the contribution of everything. So we cannot fully separate the contribution of the atmosphere, ocean, and the land. But what we can get at with these experiments by comparing their skill to the control experiment is we can get at the contribution of each component's initial conditions to the skill. So again, just to be clear, if I were to find from these experiments that the atmosphere initial conditions were really important, that does not mean the ocean didn't play a role in setting those initial conditions. It means the information from the atmospheric conditions contained all of that information from the ocean, and that was sufficient to make the more skillful forecast. So this is showing you the skill of the control. This is the same anomaly correlation metric. The skill of the control that you've seen before is up here in the upper left, and this is the skill of each of these different experiments. And the key thing that you'll see is anytime there's an experiment where I set the atmosphere to climatology, so this one here, this one here, the skill is lost. So this is telling us that the atmospheric initial conditions are most important to the skill that we're finding here in Brazil. And so that is telling us that at the very least there's some atmospheric information, there's some atmospheric processes that are important. Again, not saying the ocean and land didn't contribute to those initial conditions, but we're able to encapsulate all of it in the atmospheric initial conditions to get that skill. So then the next question is, what processes and patterns are actually leading to this skill? And particularly looking into the atmosphere. So to do that and try to understand that, we did a canonical correlation analysis. And so canonical correlation is very similar to, you can think of it as maximum covariance analysis or principal component analysis. Though maximum covariance is looking for maximum covariance between two things, principal component analysis is looking for maximum variance between two things. This is looking for maximum correlation between two things. And the two things we're looking for maximum correlation between are the model forecast and what actually happened. So we're actually trying to, it's a way of sort of identifying what patterns and time series are giving us the most skill. So you can think of it as a way of decomposing the skill into the best predicted and the least predicted patterns. So what I'm showing you here are the patterns from the model and from the verification that came out as the best predicted. And they have a canonical correlation around 0.5. I'll show you the details of that in a minute. But I wanted to show you spatial patterns first. And then this is the second best predicted pattern between the model and the verification. And so, of course, we would hope that the model looks a lot like the verification, because that's what we're trying to find, is when the model looks a lot like the verification. And so you can see that it's pretty similar in terms of the overall spatial pattern of where you have positive and negative precip anomalies. The model, I'm using ensemble means, so this is going to be smoothed out a little bit, and it's also coarser resolution than the verification. So yeah, that's why you get a little bit smoother version. Also, the model's not perfect. This is a 3-week forecast I'm trying to optimize skill with, right? So there are model errors. It's not perfect. But on the whole, we are capturing something that looks like the verification, which means to me that the canonical correlation is picking up something reasonable here. And then the second predicted pattern here you can see also rather similar, but of course with some errors. So these are just the patterns, but what physical processes are actually producing these patterns? We've identified the patterns that lead us to skill, but how did this happen? Where are these? What processes are going on? So I've done this canonical correlation for all of my different experiments where I climo the atmosphere, the ocean, the land, and all of that, the CSM experiments. And so I'll show you what those look like in a minute, but I want to highlight first for the control. The canonical correlation here for the first, most of the best predicted pattern is this sort of teal color. That's 0.5. And the second best predicted pattern, that canonical correlation, is just above 0.4. And then these open X's, I applied a method to demonstrate that whether these are statistically significant. And so if you're above the X, then you're statistically significant. When I do the canonical correlations for all of the other experiments, you will see again, this supports the previous result, that anytime the atmosphere is set to climatology, I lose significance, or for the most part, I lose, or I get really close to not significant here. Basically, we lose this correlation of the first component. And then the second component even will drop quite a bit. So again, it seems like we can't get this best predicted pattern if we're not initializing the atmospheric initial conditions correctly. So they are critical to whatever's going on. So I mentioned the South American dipole early on as one of the sources of variability of precipitation in this region. And this is showing you the South American dipole pattern. It is usually identified as the leading EOF of precip in this region. So that's how I calculated up here. I'm just showing you what that looks like. And so just to demonstrate whether this is what I'm finding from the canonical correlation is basically, is it just the dipole that I'm picking out? I'm showing you the patterns for the first and second canonical correlation. And then I've done a subtraction here to show you that while this does look quite similar in some aspects to the dipole, there's some component of this that is not entirely the dipole. So basically, what else is going on besides the dipole that is leading to these well-predicted patterns? So from the canonical correlation, I also have a time series. And so I can regress any field with that time series to try to see what else is going on more large scale and not just in that region. So I've done a regression here with the time series from that best predicted component with OLR in the Western Pacific and Maritime Continent region to try to get at whether the MJO is playing a role. And so you can see this is the greenish colors are enhanced convection in that region. And so you might think that the MJO, well, it looks like maybe it's the MJO. But this is a simultaneous regression. If I do a lagged regression where it's a week before and 2 weeks before, what you'll notice is that there is no propagation of these OLR anomalies. And a classic characteristic of the MJO is the eastward propagation. So what I would say is that it does not look like the MJO is what's going on for this best predicted component. I've also done regressions with sea surface temperature anomalies. It's really hard to get rid of INSO and its impacts. So if INSO is still playing a role that I somehow had not subtracted out properly or not been able to remove, I should have seen some evidence of sea surface temperature, coherent sea surface temperature anomalies. There's also sea surface temperature anomalies in the South Atlantic that sometimes people look into related to precip in South America. But if I do a regression with sea surface temperature anomalies, I see that those regression values are basically zero. So that's telling us that the sea surface temperatures, and so even the elliptic, are not really contributing to this pattern. So then what is it? This is lagged regression, same kind of lagged regression, simultaneous on the bottom, with 200 hectopascal winds. And so what you can see in all of these at each of the legs is there appears to be some sort of wave train here. And so it seems like there's some sort of southern hemisphere Rossby wave train that is related to this precipitation, or this pattern that's giving us the best skill in precipitation. I can look at pictures like this and I can imagine a wave train or picture something from, I could draw it from almost anywhere in my mind. So really we want to be able to diagnose what is generating this wave train, where is it originating from? And I will show you that in a couple minutes. So where are these waves coming from? We see similar Rossby waves coming in that second component. Also, the second best predicted component, this my T there, predicted, sorry. You also don't see eastward propagation of OLR anomalies. The sea surface temperature anomaly regressions are near zero. But again, we do see some sort of Rossby wave train. So where are these Rossby waves coming from in these two best predicted components is the next question. So some of you are familiar with Kurtman et al.'s new TELI model that has come out. And so we're going to use this. TELI is a very simple atmospheric model, very simplified physics. I think of it as basically a dry model, we're going to give it DJF background state and DJF climatological heating, and we run it for 720 days, drop the first 100 days just in case there's some spin up or whatever. And I'm showing you here the mean U200 and V200 from the model over I dropped the 100 days, so 620 days, just the mean. Compared with ERA 5, and the goal here is to demonstrate to you that this model is not out to lunch. It's very simple, it's not perfect, but it is on Earth and it makes sense and it's pretty reasonable in its human state. So then we're going to perform a series of heating experiments with this model to try to understand where those Rossby waves are coming from. So this is the precip regression with that best predicted component global over the globe, so I can see where there's precip. And I see this is where we saw those OLR anomalies that were not propagating. This is this precip pattern that goes with that. And so I'm going to use this to identify, to basically create heating anomalies to go into the model, to then see whether those heating anomalies are generating or can generate a Rossby wave train that makes it to South America. And so we could have remote forcing that's creating these Rossby waves. We could have local forcing. We know we have this precip going on here. It could be a local forcing. So it could be the Rossby wave trains we're seeing are coming from the precip we're looking at. So I'm going to get it heating in this region to see if the source is local versus remote. And then I'm going to similarly do that with the second best predicted component, looking at the heating in the Central Pacific, and then the localized heating from that second component in South America. And then we can compare these with the control simulation from this model to see whether we get Rossby wave trains that could reach South America. So this is showing you for that first component. So I also did an experiment where I give it all of the heating in the tropics related to that precip, so you get all of the heating anomalies. And so this shows you the model's full response compared to the control in V200 of what that looks like when you give it all of the heating. So that would have included my two locations of heating as well as any other precip related heating in the tropics. And so this is that total response. So you can see the Rossby wave here, and that came, that's sort of everything together. If you separate it or pick out just the Indian Ocean Pacific, so the part coming from here, the heating of the precip that was in this region, you see that you can capture a large majority of the full response. If you give it the heating that was local, you get basically nothing. So it looks like the Rossby wave train reaching South America can be mostly generated from the Indian Ocean Pacific region. It cannot be generated from the local South American heating. So that supports the idea that those Rossby wave trains could be coming from the Indian Ocean Pacific region to give us the skill related to that very first canonical component. In the second one, I gave it all of the heating from the second component, so this is the full response of all the tropical heating. If I give it the Central Pacific heating, I get a little bit, but very little. But if I give it the local heating in South America, I see that's where I get the stronger response. So the local South American heating explains most of the wave trade that we see in that second component. All right, so the overall question was, where is subseasonal precipitation scale in Brazil coming from? So we found for time scales, it's at least in some models, we have a strong subseasonal component, and it's not so much interannual. We found that primarily December, January, February, and September, October, November is when the seasons when those occur, that precip occurs, or that precip scale occurs. We found that the large majority of the contribution comes from the atmospheric initial conditions. Again, I'll reiterate for those of you who love the ocean and the land, I'm not saying that they're not playing a role. And then for the mechanisms, we found that it's not the ENSO or NJO. We found there's a contribution associated with the South American dipole. But we also found this very, the Rossby wave trades from the Indian Ocean Pacific forcing heating is really contributing very strongly to the skill in this region for this most significant component. So that's the story I have for you about answering the question, where is the skill coming from? So thank you very much.
Thank you, Kathy. All right, questions. Are there any questions online?
No, only applause.
Only applause. Okay, great. Brian. All right.
Brian.
Kate graciously asked to, or offered to move us around, but I'm not going to get it.
Interesting and nice talk. When I see dipole in Andes and Eastern South America, I figure, I might imagine the zonal wind is involved, and whether that's the Walker cell being stronger and weaker, or even the zonal mean zonal wind, which has a long time horizon, long predictability. But you're looking a lot at V wind. I mean, it seems like would you have noticed if the zonal wind were the reason for this?
I looked at zonal wind as well, but the zonal wind, it just wasn't like. So I did these lag regressions with zonal wind, and there was just nothing stood out as a clear, clear information about what could be, how that could be driving, these two different components. Right, this is the first component. There was just nothing that stood out, and when I looked at V wind and saw the Rossby waves, that's where I really saw something that looked like it could explain what was happening. But
That's V, right?
No, this is V. I don't have U with me, but I did look at U, and there's just nothing that stood out as
And like U850, not U200.
Yeah, of course, absolutely, I looked at U850. I didn't see any evidence that was playing a significant role.
Okay, thanks.
Just talk. It's for the people online. Yeah, you can speak up so Kathy can hear you.
Thank you, Kathy, for the talk. I would think that for that region, what would be impacted more impacting would be the location of the ITCZ in the Atlantic, and maybe related to sea surface temperature anomalies in the North Atlantic that would drive this migration or unusual migration of the ITCZ there. So do you have any comment on that?
Yeah, so as far as sea surface temperature anomalies, I just didn't find any. So I'm not saying that that's not an important source of variability. It's not. It doesn't seem to be the source of our skill, right? So that's maybe a driving source of variability. Maybe the model doesn't pick that up well, so we're not getting skill from it. So I'm not seeing the sea surface temperature anomalies playing any role in these better predicted components. As far as the ITCZ, I would assume, my best guess is that the ITCZ is playing a fairly large role in where the dipole is setting up, right? So the dipole component of this is probably, the ITCZ is contributing to it. But I also suspect that we're not picking that up very well. Again, this is getting at what we can predict well. It may be there's important sources of variability that we are not predicting well, so they would not have come out in this analysis. So it may be that the ITCZ is something, that variability is that the model doesn't predict well, so that is not one of our larger components of skill that we're finding in these patterns. So I absolutely think that the ITC is playing a role in the precip in this region. I just don't think the models can pick that up very well.
Thank you, Kathy. My question actually follows off of that and thinking like from the forecasting perspective. Do you see that it would be then the Indian Ocean Pacific region that needs to be better represented to increase that skill? Or do you see something else to actually bring this into the forecast?
Yeah, that's a good question. So I actually think, this was meant to be a diagnostic of where is skill coming from, and it does nothing about it tells us what we need to do to improve the skill. And so it seems to me that the Indian Ocean Pacific region, that's actually giving us skill. The Rossby waves generated from that are likely giving us the skill that we have. I would say that to improve skill, there are, obviously there's some models that seem to lose all subseasonal component of the skill. When you remove the interannual variability, you have no skill. So there's some models that obviously have a problem with capturing this Rossby wave response and behavior. So those models obviously need to improve in those areas. We have a model that captures this, but I would say that the dipole is such an important source of variability in this region that it's the number one source of variability. It comes out as our number one principal component, right? In EOS. So I would say that improving there does need to be an improvement in the ability to represent the dipole as the number one source of variability, and I think probably the model is not capturing that as well as it should. But clearly we have models that are not capturing what the CSM can capture, and those certainly need to be improved as well.
Other questions? Yes.
This kind of is going on the topic of the model variability and how well it's capturing its dipole. What was the criteria for the selection of the models in the first place? And I'm just curious because I'm not actually super familiar with Ben's new telemodel. So what made you choose that for the tool then to investigate these diagnoses?
Yeah, good question. So the models that were selected all came from the subseasonal experiment. Those are models for which we had hindcasts from SubX. And then the NCAR CSM, they repeated the same set of hindcasts with CSM, so we had those as well. So it really was an availability choice. And then why did I choose to use the tele model? I had gotten to this result. I had gotten to this result when the tele model came out. When I was involved in the paper, so when I first got access to tele model and what Ben was doing with it, and saw an opportunity to basically, I got to this result, and I'm like, okay. When I said I could imagine Rossby waves coming from anywhere, I really could. I was like, well, is it from here? Is it from? I was like, where are these really coming from? And so it really was just a very timely. There's this model I can play with, and I can put heating in and see if Rossby waves could be coming from there. So it really was just a timeliness. I got to this, and I was like, I don't know what to do next to answer this question. And then the tele model was available, and I'm like, I see a way to answer this question.
Any other questions? Okay, let's thank Kathy.
Thank you all.